Hello everyone, welcome to the session 1 of week 3. In this session, we'll learn about various powders for which additive manufacturing can be done. That means various alloys that can be printed. We will learn about which metal powders are available, how those metal powders are prepared, and how those powders are recycled. We will also talk about what properties are needed in those powders so that they can be used for 3D metal printing. There are typically two methods of powder manufacturing. We'll talk about those, and later we'll also learn about how the used powder recycled, and depending upon the properties that we need in the final build and depending upon the method that we are using for 3D printing, these powders are manufactured. Starting from a raw material, we need vacuum melting most often because we do not want the final powder to be contaminated. In some methods, the powder can be made even without vacuum. Most common method is with vacuum. The liquid metal is atomized first so that fine powder particles can be made. That is what we need for 3D printing. Those fine particles are collected in solidified form, and since as a result of atomization we get a wide range of powders, we need to classify them. We do sieving and other operations and bin those powders for specific purposes. The powders sometimes may be used as they are made after atomization. Sometimes they need some post processing, and blending or conditioning is one of such processes. After blending is done, we need to do quality inspection, and only when the powder is of certain quality we pack it for final use. Atomization is the key process here. Atomization means we divide the larger chunk of liquid metal, or we disperse the molten metal into particles using some method, and one of the common methods is use of rapidly moving gas or liquid stream or some plasma. There are two methods that we will discuss here. One is a plasma atomization and the other is a gas atomization. And as a result of both of these processes, we get powder particles. Depending upon the process energy or the medium in which we are doing atomization, the quality of powder is affected. In gas atomization, we have a melt pool, and from the melt pool the metal is dropped in small chunks, and this small chunk of liquid metal interacts with a high velocity gas, and this gas tears the metal chunks apart and breaks into small particles like shown here. As these small liquid particles now fall in this cooling chamber, we have our metal powders which are collected in this collection chamber. The smaller particles which can fly in this high velocity zone, they come in this area and they are collected in another chamber. In case of plasma atomization, we have liquid metal which can be made either using some electrode or some form of liquid metal pool. This liquid metal pool interacts with a plasma which can come from a plasma torch and is again shredded into small particles. As these particles go down in a cooling chamber, the particles are collected at the bottom, and we have a vacuum pump here which essentially creates the flow and also makes sure that there is no unwanted gases, for example oxygen, hydrogen or nitrogen. By the way, this plasma essentially is a mix of electrons and ions, and these are all high energy particles, and that is what causes the melt pool coming from, in this case, a titanium wire to be shredded into small particles. Usually the size of the particles that we get as a result of plasma is much smaller, powder quality is slightly better, because plasma torches produce much controlled and more energetic source of flow. Here is a simple comparison between various methods of atomization. We have water atomization, we have gas atomization and plasma atomization. We have already seen to some detail what is gas atomization and plasma atomization. The water atomization essentially uses a water jet cutting technology. That means it splits the feedstock into small particles, and as we know that when we are doing this cutting operation, the particles that we achieve may not be essentially spherical particles, and that is one of the drawback of this method, that the particles are of irregular sizes, the sphericity is not good, and more satellites are present. Satellites means that if you have a spherical particle, there may be some smaller particles attached to it. In this case, the particles may be of more irregular sizes, and some satellite particles, smaller particles may be attached to it, right. We get a wide range of particle sizes. We have from 0 to 500 micron. In gas atomization, we can get up to 500 micron, and in plasma we get up to 200 micron, and like I mentioned earlier, plasma atomization has a tighter control on powder size distribution. In water atomization, we also don't need very expensive feedstock. Like in plasma, we first need wire. In case of water atomization, we can start with the ingot, which is not very expensive, right. We do need post processing. Since we are using water, this water needs to be removed, because not all the metals are non-reactive with this water. Some may show oxidation or some type of corrosion, so we need to remove this water before that powder can be used for 3D printing, right. So only the metals which are non-reactive with water can be used in this method. For gas atomization, we have wide ranges of alloys available. We can use vacuum with this method, so even the metals which are reactive with water or humidity and so on, those alloys can also be used. So it is suitable for reactive alloys. It is also a high throughput method, because gas is a much cheaper medium, so we can use it for larger amount of powder production. And in this case also, we do not need to prepare ingots for any specific shape or sizes. In this case, we have satellites present. We have lower yield of powder between 20 to 150 micron. That means larger fraction of powder is from 150 to 500 microns. So for the 3D printing methods where we need smaller sizes of particles, this method of gas atomization does not work very well. We can produce powders of nickel, cobalt, iron, titanium and their alloys. One electrode induction melting process is used to create the melt pool. Using plasma atomization, we can create extremely spherical particles. We need to prepare the feedstock in wire form first, and that's why we need to invest in that, and the feedstock is expensive as compared to other two methods in this case. Ti64, titanium 6 aluminum 4 vanadium alloy needs sophisticated particles, smaller sizes, no oxidation, because titanium reacts with oxygen very quickly. This method of plasma atomization is preferred for Ti64. Now we will look into various metal powders that are typically used for 3D printing. Many vendors use titanium alloys, nickel alloys, aluminum alloys, cobalt chromium alloys, various steels, and various custom made alloys depending upon the applications. And here is a summary of the most typically used powders at Wipro 3D. We have this table showing various material bases and which alloy grades of each material base are used at Wipro 3D. For example, we have nickel alloys, Inconel 718, Haste Alloy X, we have Inconel 625. Various iron alloys are used, stainless steel 316L, 17.4 pH stainless steel. We have 15.5 pH stainless steel. M300 maraging steel. This 300 means its tensile strength in KSI, and similarly there are many other M series maraging steels as well. We have Ti64 alloy that is made, grades 5, 23 is additional extra low interstitial Ti64, and aluminum silicon 10 magnesium alloy, which is aluminum cast alloy, is also printed at Wipro 3D. There are various customized alloys that are basically being developed or have been developed already during as part of the material development program. Various iron based alloys have been developed. A286, which is a heat resistant steel similar to what we mentioned earlier. We have SAF 2507 super duplex stainless steel. This is Sandvik austenitic ferritic super duplex steel. Based on customer requirement as part of joint research and development, many other alloys have been developed at Wipro 3D. Some alloys are currently being developed. For example, nickel based CM247L currently is being developed at Wipro 3D. When we make powders, we need to make sure that the powders have been made as intended, as we planned them, so that our parts are of the same quality as we had planned them earlier, right? So we do analysis, chemical analysis of these powders. There are various techniques available for composition check. We have inductively coupled plasma method, ICP, for composition measurement. We have inert gas fusion, and we have wet chemical analysis, right? So using one of these three methods, we can make sure whether the elements that we wanted in the powder are available and are they in the same amount or not. Apart from that, we also want to know that oxygen, nitrogen, hydrogen or ONH content is within limits or not, because oxygen, nitrogen and hydrogen, they all are they are good only up to certain limit. In most cases they are absorbed in the powder so much that they cause brittleness or deterioration of properties, so they need to be controlled. They are small atom elements, so they act as interstitials, and when they are above a certain threshold in the composition, they cause detrimental properties. These elements are very reactive to most metals. For example, oxygen is very reactive to titanium and aluminum. In both cases, in aluminum it makes oxide, in titanium it acts as interstitial, so it causes brittleness, loss of ductility and loss of toughness. These elements can be picked up during any stage of the powder manufacturing process or even the part manufacturing process. These elements may be introduced when the powder is being atomized, if the vacuum is not proper or other conditions are not proper. They can also be picked up by the powder during handling, or even when the part is being made during 3D printing, when the powder bed is being formed and so on. So it is important to keep track and to follow the standardized procedures to make sure that the content of oxygen, nitrogen, hydrogen in the powder is not beyond the allowed limit. We have certain equipment to measure the quantities of these elements. Analyzer, The particular model which is shown here is Ultra ONHP. It can detect oxygen, nitrogen and hydrogen within certain limits. So 0.1 ppm to 2% oxygen can be detected, or 0.1 ppm to 2% nitrogen can also be detected. Hydrogen, if within 0.01 ppm to 1000 ppm, can be detected using instrument, this particular instrument. Once the powder is made, it is important to make sure that the powder particles are within certain range, or they have certain volume fractions of various parts of the total range. So that means a particular powder size distribution or particle size distribution is to be maintained in the powder that we are using, because it is essential for ensuring that the porosities are not too much and the bed is formed nicely, so that when the 3D printing is happening, the liquid metal is going through all the possible crevices or voids that are formed in the powder bed, so that the part is solid, right. So when we assess particle size distribution, what we do is we make small bins of various sub sizes or sub ranges of particle sizes, and then we calculate how much fraction of all the powder that we have lies in that small range. That is called particle size distribution, right. So essentially it says what is the percentage by weight of each fraction into which a powder sample has been classified with respect to sieve number. For example, if you have, let's say, 19 micron to 48 micron powder, that means the minimum particle size is 19 micron and 48 micron is the maximum particle size in your powder. You can divide it into, let's say, 10 bins, and then you can calculate how much volume fraction of the total volume of the powder is in first bin, how much volume fraction is in the second bin, how much volume fraction is in the third bin, and so on, right. This type of chart, which is called powder particle size distribution, tells you what type of powder particles are in largest volume fraction, how much volume fraction is of these smaller particles, and so on. And using this distribution, you can tell a lot about the properties of the powder. Here D50 represents that 50% of the powder particles are below 30.5 micron size. D10 says that there are about 10% particles which are below 19 micron size, and D90 says that 90% particles of the total powder using which this analysis has been done, they are below 48.15 micron. We want to assess powder particles in this particular fashion because we want to classify powders so that they can be used for particular application and also for a particular process. For example, laser powder bed fusion uses 15 to 63 micron particles for best properties and process. Electron beam melting can handle larger particle sizes, 45 to 106 micron, and we have learned that already that in electron beam melting larger energy is used, there is larger interaction volume with particles, that's why it can handle larger particle sizes. In metal injection molding, you need less than 38 micron particle size. There are various methods using which you can figure out what is the particle size distribution of the powder. We can use laser diffraction, or we can use simple sieve analysis, right. There are various effects of the powder sizes. It influences what is the minimum thickness of the powder bed that we prepare. It also influences the flowability of the powder, and flowability is also important aspect because the way powder is discharged from the dispenser to make a bed tells a lot about the ease of powder making or even evenness of the powder that is available in the bed. If the particle size is coarse, particle distribution is coarse, the final part will show large surface roughness. It will show low density because the powder bed will not be compact. There are only larger particles, smaller particles are not available to fill the gaps, and obviously the structure will be more porous. If you have finer particle size distribution, the structure or the bed also, they will be dense, the structure will be less porous, and obviously the surface finish will also be good, right? When we do particle size distribution analysis of the powder, we set some benchmarks, and only when the particles are within that specification or limit, we accept the powder for 3D printing. An example is shown here. We have two analysis results, result 1 and result 2. Result 1 is shown in the chart shown above. For a particular application, we have set some benchmark. That means the D10% will have 20 micron limit. That means D10% can have maximum particle size of 20 micron. D50 can have maximum particle size of 30 plus minus 5 micron. D90 can have the maximum particle size of 50 plus minus 5 micron. A sample of a powder is taken, an analysis is done, and the result is shown here, result 1. Result 1 shows D10 to be 19, D50 to be 30.4, and D90 to be 48.15, and that means that if you take 10% volume of the powder for which you have done analysis, the lower 10% volume will have maximum particle size of 19 micron. So if you take particles of 19 micron and lower, that will make 10% volume fraction of that powder. Similarly, if you take particles of 30.40 micron and below, that will make about 50% volume fractions of that powder. If you take particles of 48.15 micron and below, that will make 90% volume fraction of all the powder that you are analyzing. In result 2, we have a different type of powder in which the particle distribution is such that if you take particles of 19.35 micron and below, then it will make 10% volume fraction. If you take 30.5 micron particles and below, it will make 50% volume fraction. If you take 47.50 micron particles and below, that will make 90% volume fraction. This analysis of particle size distribution can be done, as mentioned earlier, using laser diffraction or using sieving method. An example instrument is shown here. This is PSD sieve analysis. The particular model that is shown here is a sonic sifter, where the sieves are vibrated using ultrasonics. This particular instrument uses ASTM B214 method, and any powder which are of greater size than 45 micron can be classified using this. Morphology of the powder is also very, very important. As we choose the atomization methods, the morphology changes. Thus, the behavior of the powder in the powder bed or during flow also changes, and all these things also change the material properties. We want high degree of sphericity because high degree of sphericity gives good packing and flow of the powder. We want minimum satellite content because if more satellites are stuck to the powder, the packing of the powder particles will not be good. And we also don't want any open porosities because the metal flow will not be consistent if there are porosities within powder particles. Some of the liquid metal will enter those voids instead of filling the gaps between powder particles. Two examples are shown here. As mentioned earlier, plasma based atomization gives more spherical particles, more consistent low amount of satellites. The right side picture shows gas atomized powder particles, and you can see there are a lot of satellites. Small particles are stuck on larger particles. The packing of the powder is not as good as we see in plasma atomization. If we have good powder, good surface, low satellites on the powder particles and so on, we have good flowability, nice packing, high density of the bulk. And tapped bulk means as you pour in a vessel, or when you shake it a little bit. In both cases it is high dense powder, and such powders can be used again, high reusability. This bottom image shows a scanning electron microscope of the powder particles. We have some defects in some powders. For example, open porosities are there. We have split caps, some surface is missing from powder particles. There are some elongated particles, lot of satellites. We have irregular particles, not spherical, we want spherical, and some particles are broken, right? So we have discussed powder size distribution and powder morphology in fair detail. Apart from these two properties, there are many other properties which are important for formation of powder bed and also for the properties of the final component or build that we are trying to make using 3D printing. Let's take a look at those properties more carefully. Of course, the first one and the most important one is the chemical composition of the powder. Chemical composition of the powder ensures that we get the right composition in the finally made part. Thus, the chemical composition of the powder has to match with the composition that we want in the final product. Apart from that, the chemical composition of the final part may change if the powder has not been handled correctly or carefully. We have learnt so far that when the powder is handled or is being used in machine in various 3D printing processes, oxygen may react with the powder or some other elements may react with the powder. Some unwanted elements may join the powder particles, and thus the composition of the final product may change, right? However, if we keep a tight control on the chemical composition, this chemical composition ensures that the printed part exhibit the expected material properties for which the composition was chosen. Powder size distribution, the mean size and distribution both are very important because they decide the packing, the flow and the ultimate property of the product, right. So, controlling particle size, mean size and the distribution is crucial for achieving uniform printing, a good quality product. And also it affects the way heat is transferred to the particles, the neighboring particles, and thus to overall build. It influences the flowability, the packing density and the final part density. Good particle size distribution also decides how many porosities, mean size and distribution both are there in the final product. So, this is also an important virtue of the powder. Morphology, as we discussed, is also very important. There are defects which can change the morphology. Sometimes as a result of the atomization process, morphology may change. There may be non-spherical particles, there may be particles which have void. So, all that has to be avoided, and morphology also has to be controlled, right. So, it basically refers to the shape of the metal powder particles. It influences packing density, as you have learnt. More uniform sizes of particles define or govern the right packing, better packing of the powder bed and thus the final product. Layer uniformity is decided by the morphology. Melting behavior is decided because ultimately heat transfer and temperature distribution, all of that is defined by the right morphology of the powder particles, and thus it also impacts the final part quality. And when I say quality, it defines not just property but also many other properties, like it may have the right hardness, but it may not have the right compactness, right? Wherever there is no void, there may be good hardness, but we don't want any voids in that part, and so on. Some more properties that are important to note are flow rate of the powder. Flow rate is of the powder is the rate at which metal powder is delivered during the printing process. Uh, Flow rate affects the spreading of the powder on the bed, what is the build rate, and how much powder particles are able to overlap with the already put powder. Overall, all these virtues influence the build quality. Apparent density we have learnt already. It is the amount of powder that can be filled in a given volume without tapping. It defines what is the compactness of the metal powder, and a better packing efficiency influence the mechanical properties, because if the compactness is there, then there will be no voids and the build part will have low tendency to fail, especially in properties like fatigue life. Compactness of the powder is very important. The tap density of the powder measures how much powder can be filled in a given volume with some tapping, shaking or vibrations. It is important for evaluating powder flowability and its behavior during the powder bed formation. Overall, it also governs the quality of the part, because the distribution of powder in the bed is defined by the tap density, because the lower layers of the bed are affected by how much powder is available on top of those lower layers. So the lower layers of the powder bed actually show tap density, and the upper layers more or less show the apparent density. Apart from learning about various properties of the powders, we would also like to learn reusability of powders. We want to know about reusability because it can make the overall process of printing cost effective. If we use used powder by some blending and cleaning and reprocessing, it will definitely reduce the material cost and thus the cost of the finally built component using 3D printing. This also makes the process sustainable because we are recycling the powder, we are minimizing the waste and optimizing the process, the powder usage. Thus, the process of printing will become more sustainable using these recycling practices. We also want a consistent quality of the build part. By using same batch of powder, by recycling, some blending and cleaning, we can maintain the part qualities and also uniformity of the powder used across various built in a single batch. However, achieving these goals of reusage of the powder, there are some challenges. The morphology of the powder particles may change. During the first cycle of printing, the particles may not be spherical anymore. They may have some open voids within particles, and some more satellites may have come because of the printing process itself. So these powders need to be blended and processed again before reusage. There may be some contamination. So during the printing process or handling during recycling, some particles may have reacted with unwanted materials, some particles may have oxidized, all these defects may come in. So we need to make sure that the powder is not contaminated. If it is contaminated, then we have to find solutions to remove that contamination. During handling, different type of powders may also get mixed if the powder was used with another type of powder during printing itself. Sometimes we would like to print multi-material builds. So in that case, there are higher chances of mixing of powders. So once the powders are mixed, it is difficult to separate the powders. However, possible in many cases, so that also has to be figured out for good reusability of the powders. Metal powders come with their own certificates, and those certificates ensure that the powder is of good quality and is suitable for printing. These certificates are called mill test reports or mill test certificates, so called MTC. There are various properties listed in these certificates, for example, water content, skeletal density, morphology, whether it is spherical or what is the symmetry, what is the aspect ratio of the particles. There is a particle size distribution, what is D10 value, D50, D90 as we discussed on the previous slides, how much of the particle are greater than 63%, greater than 75% micron and so on. What is the chemical composition of the powder, right? Also, what test method has been used to determine these properties? For example, whether laser diffraction was used for determining D10, D50, D19 powder size distribution, whether ICP OES was used for chemical composition measurement and so on. It also lists what are the allowable limits of these properties that are listed in MTC, and what are the results for the given powder which is in the package, right? And also it says that the test results are okay or not okay. If something is not applicable, it is mentioned there. Of course, if the powder is of good quality and it has gone through all the checks, all the items have to be okay if it is claimed in the MTC. Sometimes the properties are updated, additional properties are added. So MTCs also come with amendments. For example, amendment to MTC type 3.1. MTC 3.1 is one type of certificate, and this particular amendment example says that analysis of powder was done to make sure that the powder is clean. It says that the powder is visually free from foreign materials, it is in uniform condition, powder shall be predominantly spherical and low levels of agglomerate. There are no satellites, particles are not joined together, there are no needle shaped particles or low needle shaped particles, and there are no entrapped porosities, right? Also there are low deformed particles. So such amendments can be added to existing MTC reports if they were not part of the original standard MTC, right? So with that we end this session. Thank you for listening. We will continue with the various case studies in the next coming sessions.